Welcome. Welcome to week 7. We're getting there. How's assignment 5 going? It's all right, hopefully. This one's the first threading assignment, obviously, and it's got some nuances to it. You definitely have to think about locks, and you have to think about semaphores, and you have to think about mutexes, and we've thrown in all that stuff about, oh, you have to make sure that you only have so many threads and this and that, and that's all to test your ability to use semaphores. RSS news feeds are something that we don't really use too much now, but about, I want to say 6 or 7 years ago, it was kind of the rage. Like when these came out, it was this big deal of like, this is how you're going to read your news from now on. You're going to get all these feeds, and it's going to be all these little snippets of news that you can go read the bigger articles and all that. And everybody thought it was cool, and then we all used it for about a week and then went, this is boring, we like the old way, and just kind of went back. But lots of places still have these RSS newsfeed services, so you can get a newsfeed reader, which is what you're building, to actually create that. Okay, hopefully it's not too bad. It is due Friday. What I think I'm going to do is we're a little behind on the assignments only because the midterm happened and I wanted to give you a little extra time in the last one. So what we're probably going to do is I'm probably going to release the next assignment maybe Thursday, give you a slightly smaller assignment than what we were thinking before. I've got to work all the details out, and then we'll get back on track because the last 2 assignments, 7 and 8, are pretty meaty, good ones, but pretty meaty, and I wanted to give you enough time to wrap your heads around those without making it feel like it was you're going a little crazy. All right. But even though we are still in the midst of threading for assignments, we are moving on to new and hopefully interesting material. We're talking about, if the little thing, there we go, we're talking about networking today. So this is kind of the next big thing and pretty much the last big thing that we're going to talk about for the quarter, actually. We're going to talk about networking, which is connecting 2 computers together through kind of similar to a read-write mentality. It's very similar to creating a pipe between 2 processes, but now we're creating this kind of glorified pipe between 2 computers. And it's how the internet works, and it's how the World Wide Web works, and so forth. So we're going to see a little bit how to do it. By the way, if you really like this stuff, CS 144, is it, networks? Yeah, 144 is networks, which goes into obviously much more detail than what we're going to kind of touch on in this class. And I think you'd enjoy that. By the way, if you've enjoyed the other stuff, then operating systems, which is 143? 140. No, sorry, 140. What is 143? Compilers? Yeah, compilers. Compilers is also a great class, by the way. And then 140 is the operating systems class, which goes into like how do you build a threading library, and how do you build multiprocessing into an operating system, and that sort of stuff. If you really didn't like that, then maybe stay away from those classes. Go take more AI or whatever. But anyway, if you do enjoy it, there are lots of follow-on classes, and we'll spend some time talking about those soon anyway. So let's talk networking. What is networking? Well, it's like I said, it's basically connecting 2 computers on a network. And that network can be very local. In fact, networking can happen between 2 computers on the same, or between 2 processes on a single computer, much like a pipe would, but it's using network protocols instead of the underlying pipe protocol. So you can network between 2 processes on one computer, but most often we're talking about multiple computers talking to each other. Okay? The way that works is you need one of the computers to act as a server. And a server is simply a computer that's waiting around for some other computer to ask it something. Waiting around for some other computer to say, can I connect to you? And if you don't have that server set up, you can ask all day, but the other computer is not going to respond. Okay, so that's what you have to have. You have to have a server, and then you have to have 1 or more clients which are connecting to the server. Okay? And the World Wide Web works this way. If you connect to cs110.stanford.edu, you connect to a web server, and you are the client, and many of you can do that at the same time. So when I say that it's the same time, we do have to think about efficiency here, because there's going to be some kind of ability for, there has to be an ability for the server to get the information back to the clients quickly, and there might be lots and lots of clients. So we have to think about that. At first, we're not going to worry too much about it, but then we will eventually think more about that. How does networking work? It works through this thing called sockets, and a socket is a number. That's all it is, just an int. In fact, it's an int that goes from 0 to 65535. In other words, you can only have up to 64 kilo sockets open at once, 64,000 or 65,000 sockets open at once, which would be many more than you probably have. Most computers do not have that many open at once. But it's just a 16-bit integer, so that's why it's limited to 65535. And you basically set your program up to say, hey, listen on this socket or port, another thing we call it. And when another computer, the client, wants to connect to your server, the operating system notices this. There's lots of operating system and hardware support for this. The operating system notices this and then sends a little wake-up message to your server that says, hey, you've got a client, deal with it. And that's what we're trying to do. Okay? You can kind of think of the port number or the socket number as a virtual process ID. Okay? So you can kind of think of it that there's some socket here that connects you to a particular process on the server. Okay? That's the way it goes. All right? And the reason we don't have it do like why not make just the process ID the socket ID is because you want to say, hey, listen, tell people, go listen on this particular port, and that changes every time you do a new process. So that's how we're going to do it. How might we look these up on your computer to see what you're connected to? Well, we can do the following. We can do, let's see, hang on. There we go. We can do, let's do it over here, netstat, and then I always forget what the ones are, PLNT, -PLNT. Make this a bit bigger so we can see the whole thing here. Okay, and let me make it so that it comes out nicely, like this. There we go. That's very nice. All right, so what you can do is you can do that on the Myth servers, and it looks like the Myth servers are listening on a whole bunch of ports that are that you are able to see what they're listening on. Okay, they're listening on port 25, which is, let's see if I can get my cursor here. There you go, port 25. Okay, they're listening on port 587. Those happen to be associated with the mail server. So all the Myths listen on a mail server. Your computer listens on a mail server. Okay, this one is listening on 53. Did I write down what 53 was? 53 is the domain name service. So when you go to www.google.com, well, somebody needs to translate that into a number because your computer is dealing with numbers and people like to deal with words. So that there's a translation layer there, which is handled by the domain name service, which is running on your computer, which connects to another computer, which has all the domains on there. Like your computer kind of keeps a little list of where do I go first, and then that queries another computer, which eventually gives you back the name. I guess in some sense it's like the directory search for your the file system programs. It's kind of what's going on there. Okay, port 22 is for telnet. For SSH. We'll talk about telnet in a minute. It's for SSH, which is when you SSH, it goes to port 22 by default. Some people like to set their computers up to listen on some other port for SSH because port 22 tends to be one that lots of bad actors try to connect to because they know that if they can figure out a password, they can get into the computer. So they changed that, but ours is just the default 22. 631 happens to be the printer server. In fact, you may not know this, but you can generally on your computers, let's do it in a new window here. You can generally go to, let's make this a little bigger here, 127.0.0.1, which is your local computer. It's always your IP address, :631. If all works right, there's the little printer details. So it's actually a web server that you are listening to actually do printing. And it happens to be set up on many computers. And you might get a little message that says not set up, and it tells you how to set it up if it's not. We could also have typed localhost :631. Localhost is, as you might guess, your own computer. Okay, and it should also come up there. That's what's going on there. Okay, so that's that. Let's see, we've got another little 22 and 631 in there for TCP6. So it turns out that normal IP addresses are 32-bit numbers. They've got these colons in them, you know, like 127.0.0.1. That's a 32-bit number, just kind of separated up into little 2-byte numbers. But it's a 32-bit number, and with 32 bits, how many different IP addresses could we have? 4 billion about. There's actually more than 4 billion computers on the internet. Back when the internet was designed, which was, it turns out it was a Defense Department program back in the day. In fact, I don't know if I showed you this before. Original internet. Let's see, there should be some images here. I should be able to find out. Let's see, where's the good one that I always like to use? Is this the one? Yeah, this might be it. Yeah, that's a slightly, there's the one I was thinking of. Oh no, that's it. That's the tiniest little one. You can't see it on there. Well, you can kind of see it. Stanford is on there. We were part of the original internet. Nice, right? Notice who's not there. Somebody else relatively local, not there. MIT is on there. BBN, which is one of the original places. It's a company that kind of started all this. Let's see. Carnegie Mellon was on there. It used to just be the Carnegie Institute at that point. Illinois, Utah was on there. Utah, believe it or not, has a really good computer science department. And back in the 1970s, they happened to get on the internet really early. So lots of early things. But anyway, back then, they said 32 bits, 4 billion computers on the internet. That'll never be that many computers on the internet. That's ridiculous. So that's why they kind of started out with 32-bit numbers. But of course, today we don't do that. How do we get away with this now? What we have is routers that then give, like in this building, there might be one IP address, and then the router gives each one of you a local IP address, and so it's one level removed. So that's what's going on there. We are trying to fix this issue so that every computer can have its own email or its own IP address. We do that through IP version 6 versus version 4, which has a 128-bit address, which is many more computers. You could practically, in fact, I think you could probably give every atom in the universe its own IP address if you wanted to with that many numbers. So there's lots in there. So there's plenty of room to grow with that one. But it's going to take a while to get everybody up to speed. Some servers are listening for that. Okay, now, if you happen to be running a program yourself, notice that over on this side it says PID program. It doesn't say anything. That's because it kind of hides it from non-super users, which we are not as just regular users. We can actually, let me run something we're going to actually create here, time server descriptors. I think that, there we go. So if I do this, it has to be on the same computer. What are we on over here? Myth 58. So let's actually do it on the same one. Let's do, oh, I'm at Myth 58. Okay. Let's do it again, and oh, look at that. It says 2655/time server, and then it doesn't give the whole thing, but that's ours. Like, that's the one I'm running right now. Okay, so that happens to be port 12345. It's kind of nice. Yeah, Anna.
Why is that one 000012345 and not 127?
That's a good question. Why is it 000 instead of 127? I don't know why, to tell you the truth. I'm not actually sure why that's wrong.
Why are we 127?
Why are we 127.0.0.1 is the way the internet says local computer. That's just the number it gives to all local computer. Your local computer is the same as every other local computer. I don't know why. It's a good question. I'm not sure why it says 0.0 up there. But anyway, the port is correct. But you're right. The other part is not. Okay. So what else can I tell you about these addresses? As I said, there's let's see, there are 65,000 of them. You really only should use some in a particular range. Yeah, question, Mikhail?
Yes, quick question. Wait, why didn't it show that your SSH connection was established?
Why didn't it show that my SSH connection was established? Where?
Oh, I thought you were SSH. Are you SSH into Myth?
I am SSH into Myth. This is on the Myth computer, but it doesn't say the actual connection. Like, there might be many connect. This is just showing you which servers are available, are listening. That's all this is showing you right now. Good question. All right, so you can actually go and see a full list of common ports, okay? The common ports, if we go, there's lots of them. Okay, this is like, that's actually just a tiny little list of them here. Let's see, if I go to, here's the common ports. I'll make this a little bit bigger here. Okay, whoa, that was very big. So basically, ports 0 through 1023 are kind of used for system-y things. Like you don't want to do a port that's really low. Notice all the ones we talked about earlier were kind of low. They're like very well-defined. Don't use these ones because they're all ready for SSH and for, oh, by the way, 80 is for the web and so forth. And so there's, you want to be able to, you don't want to use those ones, okay? But there lists them all in there. Does it say up here what the other ones are? No. So we've got lots of ones. Let's look at 80 in there. 80 is for HTTP, which is the web and so forth. Lots of ports in there that you can look at that are well-defined and don't use them if you can help it. Let me go down to the next list here. After that, okay, from 1024 to 49,151, which is, you can see why they chose that number based on some powers of 2. Those are assigned ports, but it's kind of wishy-washy. It's basically like somebody says, hey, I want to use this port, can you assign it to me? And the IANA, which is like this organization that does this, kind of determines whether or not you have a legitimate reason. Are you a company? Are you are you doing something interesting? They say, fine, you can have one. We'll say that this is your port. And some of them in there, they do that. OpenVPN for like connecting your computer through a virtual private network, that's 1194, etc. Okay, but lots of them. There's thousands and thousands of these, but you don't have to live by those, right? If you do your own, nobody's going to go and, oh, you broke my thing. If you're running a program that needs that port and you run another program that's on that port, they can't both be listening to the port at the same time. So that's the big issue there. We used, for the one I just showed you, we used 12345. 12345. This happens to be set up for Cube World, Little Fighter 2, and NetBus. They all kind of, are I guess they assumed that, or they all wanted 12345. We will often use that one just because it's easy to type and whatever. But if you happen to be running a Cube World server on your computer, well, that's probably going to conflict with the one you want to do. So I don't even know what Cube World is, but anyway, you can do that. Or Little Fighter 2, whatever. Okay, anyway, and then above the, whatever the 40,000 or whatever it was, they're kind of up for grabs. They will not predefine those. You can use those for whatever you want, and nobody's going to say, hey, that was the one we kind of wanted after that. Okay, so those are the port numbers. And let's see, there we go. And those are what you'll see. You'll see a lot of normal ones, and then we'll use our own. Question? Well, that's a good question. Ports are on a server to listen to other computers. A socket and a port is kind of interchangeable. A socket is more or less, once you set up a socket, think of you setting up a pipe. That's kind of the way it is. But the port number is the socket number. You use a socket on a port number. Let's put it that way.
So can sockets be on both computers and servers? Or?
Well, a server just is a computer, right? So it's not like, yeah, I mean, when you send a message to another computer, you actually use a port, but it's not necessarily the one you're connecting to. So let's say I want to connect to your server on 12345. My outgoing port might be, 1800 or something like that, or just whatever it goes out on. And then the other computer goes, oh, when I respond, go back to that port. We actually hide a bit of that from you from here. You don't need to worry about those details quite as much for this one. It's just kind of all built into the libraries we're using. Does that make sense? Yeah. Anybody else? Good questions. Lots of details here that you can get into. All right. Let's see, what else? That's that. Let us create our first server. Okay? So we're going to create a server, and all the server is going to do is, let me do it right here. It is called time server, and we're going to use descriptors to start out, okay, to do this. And there's a bunch of setup, obviously. In here, what we're going to do is we're going to set up a server that basically gets the time on the server. As it turns out, it's going to get GMT, which is the time at Greenwich Mean Time in England. It's going to get that for, well, it gets the time and then it converts it to whatever we want. In this case, we're going to convert it to Greenwich Mean Time, which is pretty standard. It's the easiest one to type, as it turns out. But what we're going to do, what it's going to do, is going to get the time. It's going to, when a connection, when you get to connection request, it's going to find the time and then format the time into a string and then push it back to the computer. So it's basically like a time server. It just tells you the time. Okay? And that's all there is to it. Okay, how do we do this? Well, you can do int server equal, and remember the server is just a, well, in this case it's a, in this case it is a number that associates itself with a server. It's kind of like a file descriptor in that sense. Okay, and then we're going to use create server socket. Okay, 1, 2, 3, 4, 5. All right, that's it. That's all we're going to do for this. Now, the create server socket uses some underlying built-in system calls and so forth. You can go look at that in, I believe it is serversocket.cpp. Actually, let's just see. Let's see if we can find server socket. Serversocket.cpp, and oops, that's not it. Did I server? Hang on. Serversocket.cpp. Oh, .cc. No. Let's just do it here. Serversocket.cc. There we go. Okay. And create server socket uses some underlying function, a function called socket, which does, and it's got some parameters in there and things that we're not going to worry about right now. We're just always going to use these ones. You feel free to look at those. We'll talk about some of the details of this pretty soon. Okay. And then, by the way, did you notice that I did Control-Z and then FG? Now you know what that all does. Right? I've been using it all year, and some of you now you know. There it is. Okay, so we create the server, and then we basically do a little while loop that just sits here and waits for connections. Okay, so we're just going to sit here and wait for connections, and when we find, well, we're going to do the client. We're going to get the client equals accept. And then we're going to ask for tell it to accept on the server number. And then we're going to pass in a couple nulls. If we wanted to get the client's IP address, we could use those. We could use the nulls to be a couple parameters. One's like a status, and the other one's like, what do you want to get? Kind of like wait PID. We could use that for to get information about the client that we want. Okay, and then we're just going to call this function we're going to write in a second called publish time to the client. And that's it for main. It waits for, it does the accept, and by the way, accept blocks until you get an actual client that comes in. Okay, just sits there and waits. And then when a client requests the connection, it goes to the next line, it creates the connection, then goes to the next line. And then it repeats. That's all there is to it. Okay? All right. Now, if publish time took a long time, then you might start to drop connections. This is something we have to worry about. We will get there a little bit later. Yeah. It never breaks out of the while loop. This server goes on until you do Control-C. And in fact, most servers are like that. They just kind of go and go and go, and then when you want to break them, you stop the program, and that's it. Because this is really simple now. You could certainly have some other way to do this and stop it nicely, but it doesn't really matter in this case. Yeah, good question. Anybody else? Yeah.
Why do you want to do it in a loop if you just are trying to get the time once and it's going to block at accept anyways?
Yeah, good question. Why do we want to do this? This is so that we can get, you can ask for the time, then I can ask for the time, and you can ask for the time, and somebody. This is so that it's going to sit there and just anybody who requests the time is going to get the time back. So it does it one after the other, after the other, after the other. That's why we want it in a while loop. It's serving the time forevermore, as long as we have it written. Good. Yeah.
So when we were doing types and different things, we could kind of see where the file descriptors were and like how they were talking to each other. Is that something we're gonna learn, or is that all hidden in the system?
Right, so good question. The question is, like, wait, this seems a little more hidden from us than like all the file descriptors and so forth. For now, at least, and really when you're writing your programs, all you're really going to need to know is, look, have I set up a server using create server socket? And then have I accepted the server and gotten a client from it? That's really that's the level you're going to look at. Feel free to look at the header files and the actual C C++ code if you want to dig a little deeper. We're also going to use, well, we'll see in a few minutes how we're going to make it even a little simpler. Honestly, that's not the level we care about. The level we care about is create the server, respond adequately, and send it something. Okay? Question? You?
If I make a different program with the same server socket number, what's that do? Does that break out of this program and then overwrites it? Or?
Yeah, good question. Let's try it. So right now I'm listening on port. The question was, wait, what if I create two programs that try to listen to the same port? Well, this one happens to be running right now on 1, 2, 3, 4, 5 on MIF 58. If we do the same thing again and do another one on 1, 2, 3, 4, 5, also on MIF 58, it says could not start the server. So it doesn't let you. It says, oh, somebody's already using it. Sorry, and that's all there is to it. Okay, yeah. So you have to be a little careful when you're setting these up. That you don't use. So for instance, when you do your assignments with these networking clients, we're going to set up the port you use based on a hash of your username, which is unlikely to match anybody else's. So it's gonna should work out just fine. But yeah, good question. You can't duplicate it on the same machine. It doesn't work. Very good question. Okay, let's write the publish time function here. So to publish the time, we have to get the time. All right, time. And then it's actually time underscore t. We're going to look at that in a second. It's a struct that is built for you. Raw, and I don't need struct time t because it's C++. You don't need it in C++. And then we're going to just basically use the time function to pass in a pointer to this raw time, which populates it. Okay, and then we are going to use. Now we do need a different. Now we're actually doing. I guess we probably wouldn't need to do this anyway, but anyway, we're doing it this way. PT, a pointer to a time, which we are going to do that. We're going to say GM time, and we are also going to pass in the raw time. This is going to do some of the conversion for us. Okay, and there's another struct called TM, which we're going to do, and GM time is going to do that. Now, let's talk about time for a second. It turns out that if you look at time t, sorry, I said this was a struct. This is not a struct. It's actually just an integer. Time t, if you look up time t, it's just an integer. And when you ask for the time, when you say time, it populates the integer based on the number of seconds since the epoch. Okay, in fact, if we go and look this up, let's do it over in here. Let's close this. Man time, I believe this is it here. And let's see, here we go. Time returns the time as the number of seconds since the epoch, or epoch, depending on how you pronounce it, which happens to be the beginning of time in Unix world is 1970, January 1st, 1970. And you say to yourself, who came up with that number? What was the reason for making that number as the beginning of time? Well, Unix was created in 1970, and Unix was, because they did that, they said, well, we got to have the time basically from some time. Why don't we just start it now? I don't know if they never thought that there might be an issue with using time based on numbers before 1970. I don't know. They didn't think they'd use this anyway for that. But it was the time since 1970. And once again, many computers these days still have time underscore t, an integer that's actually a 4-byte or 32-bit integer. Once again, number of seconds since 1970, January 1st, 1970. Let's find out how many seconds that is. How many numbers can we fit into a 32-bit number? 4 billion, right? Why don't we just do this? We'll do it this way. Let's say, so there's 2 to the 32, which is how many bits we have, right? And that's how many different numbers we can do. It turns out this is a signed number, so it's actually only 2 to the 31. Okay, 2 to the 31. In fact, it's -1 because you don't get that whole range, as it turns out, because it's second since. So I guess there's no 0 in there. -1. That's how many different numbers we have, which is 2 billion some. Let me bump this up a little. 2 billion different numbers, seconds since 1970. Well, if we wanted to figure out how long this is going to be, right? How are we going to do this so that we can figure out how many years it is? How are we going to convert seconds to years in this case? Divided by maybe 365.25. Right? You got to have leap year in there, I suppose. Right? Okay. That's going to be the number of days per, what is this? There's seconds per day now, because we end up wanting to know the number of years. Okay. And then times 24 times 60 times 60. Oops, did I forget a parenthesis in there? Is that going to be, there we go. Okay, so 68 years, right? 68 years from 1970 gives you 2038. What's going to happen to computers that still use this time in 2038? It's going to wrap, right? This is 107 stuff, I guess. Right? It's going to wrap around, and any time after that is going to start from 1970 again. So in 2038, we're going to end up with an issue where there are computers in the world that are currently not going to be updated until then because, well, they might be. Who knows? Let's see. Some of you are actually younger than 2000. Who's born after 2000? A few of you. Yeah, a few of you. Okay, this scares me, by the way, because I vividly remember the year 2000. Anybody remember the Y2K? Or anybody know about? You don't remember it. The Y2K issue? Well, what happened in the year about 1997, people realized that there was a very similar issue with many programs where programmers would write the year with only 2 digits because they were writing these programs in like the 1970s, and they're like, who's going to be using these computers 25 years from now? Ha, 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 right? Well, banks are, right? And banks still use the computer. They use the same programs and whatever. And what they did was they wrote the date with only 2 days, mainly to save, or just 2 numbers, to save memory. Because back when they were building these computers in the 70s, the memory actually meant something. And they were, well, for every date, if we save 2 digits, that's actually a lot of memory. Back in the day, it was a lot of memory. So they did this. Well, when 2000 was going to come around, then it was going to wrap around and go back to 0, which instead of 2000 would be 1900, and then this would be a big deal. Around, the first time I heard about it was about 1997. Some people had thought about this a little bit before then, but 1997 was when most of the world all of a sudden woke up and went, oh, we're in trouble, right? We're gonna like, the entire world could collapse if all the banks collapse because all their software thinks that it's 1900 instead of 2000, and so the world will burn. And this was a big deal in 1997 or so. Well, people went and looked at all these computers and said, well, okay, we can fix these. We just have to hire people to rewrite the code and recompile it and so forth. Much of the code, believe it or not, was still written in COBOL, a language designed in the 1950s. Turns out that's still kind of true, that a lot of banking software, for instance, happens to be written in COBOL. And most of the COBOL programmers had retired. They were all living in Florida retired, right? And so they all started picking up their phones, and somebody said, hey, we'll pay you $1 million to come to our bank and fix this. And they all went, I'm on a plane. And they went and like made lots of money and fixed it mostly. But it really, people, December 31st were like storing like tuna cans and things and like lots of water and all that because they thought this was gonna, like the world was gonna blow up because of this. And of course it didn't happen. I remember one website I went to that said the date was like January 1st, 101 or something weird like that. And it was probably that issue is what happened. But anyway, that issue happened in 2000. We are coming up with another Y2K, like, you know, more, better, bigger, faster, whatever, in 2038. And there are still computers that deal with that. So all of that is to say that we still use this time_t. Some computers, like the ones we use, now use a 64-bit number. Oh, by the way, a 64-bit number would be, instead of 2 to 31, 2 to the 63. And this gives us until, well, it gives us, what is that, 292 billion more years. So if people are talking about that 292 billion years from now, it's probably not going to be us, it's going to be computers talking about it, because who knows, it's not going to be probably not going to be any humans talking anymore. But they're going to go, we've got to deal with this. That could happen. I think the sun is going to become a red giant before then, and then we're all, you know, the Earth is going to get engulfed. And I think so. Probably won't be computers. They might ship some computers off to some other solar system. Who knows? But anyway, they're going to have to deal with that 292 billion years from now. But that's that. So back to what we were talking about. All that digression aside, we are getting a time t. We're converting it to this struct tm, which kind of breaks it up a little bit. Question? Yeah.
Why would the time t be signed?
Why would the time t be signed? It's probably because you can get you want a negative like return value, and like, oh, let's just make it so we can get -1 back. That's probably the reason. Like yeah, who knows? But they also thought, well, again, 68 years. If they'd done 32 bits unsigned, we would have gotten another 68 years, which would have been kind of nice. But they didn't think about it. Probably just because of I want a return value to be -1. Probably the reason. Yep.
Is there a program in our computers that like constantly runs a while loop and changes the number?
Oh, for the time, yeah, so it's such a good question. Is there a timer in your computer is really what you're asking, right? I mean, is there a clock that's updating? Yeah, sure there is. Yep, and the timer runs at whatever your clock frequency is, but then they just divide by the number of clock ticks per computer. If your computer runs at 1 gigahertz or whatever, it just divides by 1 gigahertz to get you the number of seconds. And it does update that every second in that case for that time. That's happened. That uses a signal, by the way. Just the operating system, basically, it's a signal that happens it's a timer that happens every second. It just goes and does that. It actually happens much more frequently than that because there's other more precise timers than 1 second. But yes, there's absolutely a timer that updates every second. Yeah.
How like you synchronize I run roll at different times, so like you connect it to like a little tiny know which one.
Oh yeah, good question. How do you synchronize these timers? Using time servers, basically. Like somebody in Greenwich, England says, this is the real time, boom. And then it's a bunch of astronomers who do this, by the way, and they all say this is the real time based on this and that. And there's always leap seconds and things every couple of years we get and whatever. And they say this is the real time, and then a bunch of time servers connect to that and then have their own local versions, and then we connect to those, and it's all very coordinated. Doesn't always work, but it's pretty coordinated. Yeah. Yep.
So I got a refurbished computer from up in like Germany or something. But so the clock always resets to like sometimes in Europe when I start up, and only when it connects to the internet does it reset to the right time. And I looked it up and they said, oh, this is a hardware clock issue. So is that what is going on?
Yeah. So people who didn't hear that, so Amy got a computer and it was from Germany or something, and every time she turns it on, it resets to the German time zone or whatever. Yeah, when they set up the BIOS on that computer, it probably said, if you don't know the time, look it up by just set it to this time in some other time zone where it was first originally built. And that's a hardware sort of issue. By the way, it may be because your battery, there's a tiny battery inside your computer that might be dead. That might be the reason that it dies, does that. But then it connects to the server and it's okay once it does it. Okay. Anything else? Good. All right. So let's actually finish this program up before we can go to next programs. We are going to get the time using this GM time function, and then we're going to convert it using this GM time function. Then we're going to have to convert it to a string. Let's just use char star time string there. 128 is definitely long enough to hold our little time string. Okay, and then we're going to do strf time. This is the thing that converts the time to the actual string for you, and this is in many languages has this strf time function. And then it takes in the time string, and then what else does it take in? It takes in how big it is, size of time string, so it doesn't overwrite past the thing. %C in this case actually means not one character, but it means do it in a local defined time. And this is the GMT time that it's going to do. And then it needs to take in the pointer to the actual time struct TM that we have there. Okay, and then what are we going to do? Well, we're going to do this. This will give you flashbacks, maybe not good ones, to the midterm exam. Number of bytes written equals 0. Size t num bytes to write equals the string length of time string. We're sending that we don't need the 0 on there, as it turns out. We don't need to send that. And then while num bytes written is less than num bytes to write, num bytes, num bytes written. I always get this wrong, I have to think about it. Num bytes written plus equals write, and then let's write to the client. and then the time stir plus the num bytes written, and then num bytes to write minus num, this is becoming a long line, num bytes written. Okay, all right. And then that is in our while loop. And after that, we are done writing, and then we need to close the client. Okay, so this is actually now all of a sudden really important to do the write in a loop, because when you're dealing with networks, it's very likely that you will not push all of those bytes out to the network. Files, it's pretty likely that you're going to get them all pushed. But in this case, unless you have a pipe that's filled, another maybe like making you twitch a little from the midterm. But that's what's going on there. We need to write this to actually write all the bytes out. But notice that the client in this case, okay, the write function treats that just as a file descriptor, which in Unix it is a file descriptor, turns out. Okay, it's a file descriptor that ends up pointing to a socket that sends it to the client. Okay, all right. Let's see if I made any mistakes here. Time server descriptors. Looks okay. Okay, and then let me run in the other one over here. Time. We've seen this already. Server descriptor. We haven't actually seen it work yet. Time server descriptors is running. Okay, and you can actually get that information by connecting to the thing. I have written a little client that we'll talk about probably next time, but you can do it in an interesting way using a function called telnet, which we're going to talk about a little bit later too. Telnet is kind of, it's what used to be, or it's the original kind of version of SSH, except it was very much, SSH stands for secure shell. Telnet is very much not secure. But what it does, all it does is it connects to a network and sets up a connection, and then you can talk back and forth to the network. So if we type telnet myth58 and then give a port number, 12345, okay, if all goes well, there we go. It tells you some details, it says trying myth58, as it turns out that's the IP address for myth58. Connected to it, tells you something about how you exit out of it. All you do is you do the connection. The instant you get the connection, the time server goes, here's the time. Close the connection. And so that's what happened here. And and that's it. Okay, so there is no back and forth. We'll get to the back and forth in a little bit. But that's it. Okay, notice it is May 13th, 9:14. It's 9:14 because that's the current time in Greenwich, England, as it turns out. Okay, and 21:14 is 9:14. I believe that's correct. 7 hours difference, something like that. Who's sending messages? Hi in EOF, don't do that. Thank you though, but don't do that. So anyway, once we have the server going, now this while loop, what happened? It needed one connection, and you guys could all check that, by the way. You could go right now, telnet to myth58 port 12345 and get the actual time from myth58. Okay, you could actually do that and check it out. We could do this in a little while loop here. While one do. Let's see. Actually, let me just show you. I'll run the time client right now. I need to do myth58 and then 1, 2, 3, 4, 5, and there we go. It just kind of it takes away all the other garbage. But if we do this in a while loop, you can see that it updates. While one do time client myth58 1, 2, 3, 4, 5, and then let's sleep for 1 second. And done, and then there we go. And then every second it'll just kind of update. It might skip one because it's not right on the second or whatever. It might do that. But you can see that every second it's updating because it just updates as we go along. Okay. You can do some other kind of fun stuff with this. I wrote a little shell called, let's see, Cornertime.sh, which looks kind of weird, and it's basically calling this. Let me change. Oh, it is myth58. That's good. Here's what Cornertime does. Let me run it for you first. Cornertime just basically keeps the time up in the top left corner of your shell, right? Anybody ever wonder how Vim and Emacs actually makes it so you can type up here in your shell and not down here, and it actually does? It's using these things called ANSI escape characters. So if we look at this, let's see, ANSI escape sequences. There we go. So here's a table of all these ANSI escape sequences. It's basically these agreed upon things you have to send to your terminal to make the cursor move around. right? And you can do it. You could build a Pac-Man game or whatever and make it in the terminal, just like, you can do anything else. You can make it move around the screen, which is kind of fun. It takes these things called escape commands. And if we look back at here again, the escape character, it's actually a little weird to type that. That's actually one character. You actually have to type Control V and then the escape character, and it puts that one character in there for you. And then every time you want to print something, you print the escape character and then some command. Basically, in this case, it saves the cursor position and then moves to the top left and then makes it white with red background, so I wanted to do that, and then it calls the time client and updates it, and then it only sleeps for 0.2 seconds in this case. If you do cornertime.sh in the background, well, then you can do ls and whatever, and it'll keep coming back. Kind of nice. If you want to keep that little timer up there, of course you've got one in the other part of your computer anyway, and then we can do that. It doesn't necessarily work well with like Vim. It works okay, but then if you want, like it'll work okay if you do that, but then sometimes it goes, like if we go back up to the top, it'll probably not work. There we go. So yeah, it's not the most robust thing in the world, but that's that. Let's see. Let's get rid of that. There we go. So so you can use this time server if you want to. Okay. Did anyone try connecting to it? Did it connect? Okay. If you connected to the time server, anybody get connected to it? Yeah. Okay. So what do we want to do to make this program a little bit better? Well, what we want to do first is make the screen bigger. What we want to do first is we want to, this is a published time we already talked about here. We want to actually get rid of that whole while loop write business. That's midterm stuff. We don't want to write that, right? We want to make it easier to print stuff out to the server, and let's do that using a library called Socket++. Okay, this Socket++ library is just a library that wraps that write command and does all the buffering and whatever is necessary for you so that it makes it easier to do that. So let's actually just quickly rewrite this. No, we want to do time server. We'll keep the same one so we don't have to type all the differences here. So what we need to do is you just need to, and you're allowed to use this. It's a library that's not built into C++, but you can use it. It's called Socket++ / sockstream, which is nice. Okay, and then all you need to do down here is get rid of all this that we don't like writing, and we just have to set it up to know how to connect to talk to our client. We do the following. We say sockbuff SB, which is sock buffer, and we tell it, here's the file descriptor we want you to write out to, okay? And then we do IO sockstream SS, which is now a sock stream, which is in this library as well. And then we could do something like SS, and then these should look very familiar, time, string, and L, and it takes care of all that for us, okay? And the other nice thing is we also, because of the way this socket buffer works, when the function goes out, when the sock stream goes out of scope, the sockbuff destructor closes the client. So you don't even need to close it anymore. Once it goes out of scope, the client gets closed for you. It's kind of nice. So that makes it so you don't have to write those. You don't have to write those. That while loop that's really annoying to write. Time server descriptors again. Oh no, sock stream. Did I do it wrong here? Let's see. I think that's right. Let me just see. Time server. That'll do. It is socket++ / sockstream. Did I do that right? Oh, .h. Oh, okay, thank you. You guys are better than me at looking at this stuff. There we go. Okay, and there we go. So it's going to be the same exact socket server. Okay, all right, and that's the next thing we want to do. This is going to make it much easier, so you don't have to do the writing and waiting and all that. It's just you can use that. As long as we have a C++ program, you can use that, which we are going to do for all the rest of the projects and things. Okay, makes it easier. All right, what else are we going to worry about? Well, turns out, and let's actually try something. Let's say that we let's say we made publish time very slow. Okay? So let's say time server descriptor CC. Let's say that it might publish the time, but then it's going to be really slow. So we say something like sleep, I don't know, 2 or something like that. Nope, that's not going to work. How about 2? There we go. If we do that, let's see, there we go. And then let's say I run this again. And if we go up and do our 1 second business here, there it is. Okay, what it's going to do is it's trying every second to actually get the number, but it should, hang on. Let's see, we want to do this. Instead of, let's get rid of that sleep and see if that makes a difference. It should. There we go. So it's not sleeping anymore. Who's doing the sleeping now? That's the actual server that's got the issue. And when you try to request a client, it blocks requesting the client, and so it takes time to actually do this. We want to get rid of that delay because you don't want to have to wait for someone else's Google search before you do a Google search, right? You want to do it much quicker. Well, and actually, before we do anything else, let's actually get rid of that sleep too. So I guess we could do it later. But how are we going to do that? Threads. Okay. Now that you know about threads, you can launch a thread every time someone wants to connect to you. And remember how threading works. You're doing it now. A thread says, okay, I'm going to be in some, let's say, while loop. I'm going to launch the thread, forget about it, let it do its own thing, and then go back up to the top of my while loop or whatever, and then I can accept another connection. Okay, so that's what we're actually going to do. We are going to use a thing called a thread pool, which I've mentioned a couple times, thread pool. And a thread pool is what you're going to build for the next assignment. Okay, so we're going to use it now, but you're going to build it for the next assignment. And you're going to see how that works in the next assignment. But it's relatively straightforward about what we have to do to actually do this. Let's do this. We need to go down to main. And this while loop is where the problem is, right? We're blocking basically until publish time comes back. So what we want to do is we want to say, oh, okay, let's create what we call a pool of threads that allows us to go and set these threads up. Every time we get a request, we're going to throw it off to a thread for some maximum number of threads. In this case, we're just going to use 4, as it turns out. You do need another pound-include. Let's see if I can type this one right this time. Pound-include, I believe it is thread pool.h. There we go. And that's that. And then what we're going to do in main is we are still going to do the accept. But once the accept happens, we want to get back to that accept as fast as we can so that we don't block, so we don't like make the user wait on it. Okay? And in this case, we are going to do the following. Okay, we're going to say pool.schedule. When you write yours, you will see what this is all about. We're basically going to schedule a pool. This takes a function. Great, so we'll use an anonymous Lambda function here. We need to do the client, and then we need to do publish time for the client, and that is going to be it, and then we don't need that anymore. Okay, so now this is going to happen instantly and go back up to the accept. So you'll be able to accept many, many more clients very quickly. They will all go into their own thread, up to 4 threads in this case. We could make it 40 if we wanted to, but we haven't set that up yet. We need to do that. Let's see, thread pool 4. Pretty straightforward. You set up the thread pool, and then you can schedule threads to go off on there. You can schedule work to go happen on those threads as they go. Okay, that's what's happening there. Questions on that? Yes. Okay.
And so, like, threads wouldn't be as so they would be more efficient / not like take up as much memory as processes, and so that's why we do like multi-thread instead.
So the question is, do we do this because it doesn't take up as much resources? I think no, this takes up more resources, as it turns out, but at the benefit, with the benefit of doing it fast. So each time somebody requests the time, we go and set another thread off, or say to one of the threads that's waiting around to do work, please go publish the time. That's how we use that. Okay, pretty straightforward. Using thread pools is actually very nice, as it turns out. Yeah, easy. Does it automatically do which? It automatically, thread pool does all the joining, yeah. You'll build that into your thread pool when you do that. Okay, but the one thing that we do need to change, yeah, question?
Yeah, I was gonna ask if servers like already like create threads and like make it fast and stuff, like why do you need to create threads when you're downloading?
Why do we need to create the threads when we're downloading things? So the next assignment, you're going to see how you use a thread pool to make things a little bit faster than what you're doing now. You won't be able to tell necessarily for the assignment 5. But basically, having threads already running means that you don't have to get them running when you call it, so it's faster in that sense. They're all just waiting around going, give me some work to do, just like Farm did for your assignment 3. Yeah.
Why did we pick 4 again for our pool?
I just picked 4 because it was a number bigger than 1.
Probably know how many we would need.
How many do you know how many you need? Good question. Depends on what your load, you expect your load to be. So Google's going to have thousands and thousands of threads running because they know that millions of people are going to be, each server's got its like lots and lots of threads. For ours, I'm just making it small just to do it. We could have made it 40 and it wouldn't have mattered. You are generally limited to the number of threads on a particular machine if you're not the super user, thousands or something like that. So we don't want to do that. Now, the other thing we don't want to do is make the bandwidth of the system such that we're not going to want to like tie it up too much. This is what for assignment 5, what you're doing is you're saying, oh, I only want 24 total threads and I only want 10 threads going to any particular server, because you don't want to blast it with all your requests. That's kind of what we're trying to do with limiting these things as well. Okay, so let's do this. We have to do one other thing here. We need to actually make publish time what we call thread safe. It's not right now, and you wouldn't know that because you wouldn't necessarily think about it. But the way we're doing this, we are using one kind of globally available pointer here, or one pointer that actually tries to go to this, that shares the same time struct. We can use a different function to do this. The first couple lines are going to be exactly the same. And what we're going to do now is we're just going to, instead of making it a pointer to a time struct, we are going, or TM struct, struct TM. We're just going to make it an actual local copy of the TM struct. And then what we're going to do is we're going to use another function, gmtime_r. R stands for reentrant, which basically means it's thread safe. Why is it thread safe now? You are going to be copying the time into your local copy, thread's copy of the time, so they're not all trying to share this copy. Okay, so that's why we're doing that. And it takes a little bit more information here. It takes the raw time, and it takes a pointer to TM, which is what we're trying to do. And then otherwise, I think, except for this being ampersand TM, I think that's all we need to do to change that. Okay. Say again? Did I screw something up?
I don't think it has the ampersand.
You don't think it has? I think it has to, because it's a pointer to a time. Before it was a pointer. So now I think it does. We'll see. But anyway, that's all you have to do to make it re-entrant. You have to think about these things. When you do functions with threading, you always have to worry, can I do the function? Is it thread safe? Things like stir talk, not thread safe. Why? Because stir talk has its own internal state, which is not really what you want. That's why you should use another one. So for instance, if we look up man GM time, right? It should have, there's a whole bunch of different times in here. There it is right there, GM time _r, which is, let's see, does it say that it's the reentrant version? Yeah. The GM time R function doesn't say, but stores the data in a user supplied struct. So basically it's there. I don't know if it even, you can look up thread. There we go, tells you if they're thread safe or not. You have to think about these things when you're doing threads. Yeah.
Could you explain again why we have to change it from a pointer to a local?
Oh yeah, the question was, why do we have to change from a pointer to a local one? Well, first of all, the GM time _r function takes a pointer to the thing, but it populates it for you. So in this case, it populates it for you instead of giving you a pointer of a local copy that it's got. So that's the difference there. The regular GM time says, here's my pointer that I'm keeping the time in, the one that, I'm creating it for you and giving it to you. And then if you called it again, it would just redo that time. And so you don't want your threads sharing that one value. You want their own copy of it. Good question. Yeah.
Is there anything you can do with storing threads manually that you can't do with thread pool /
Is there anything you can do with threads manually you can't do with thread pool? Not really. I mean, the threads, you're going to want to do threads if you have no idea what your load is going to be, or you just want a one-off thread or something like that. You probably don't need a whole thread pool for it. Yeah. Once you write that assignment, you'll see kind of the differences of when you might use it or not. Good question. Yeah, Tom. Yeah.
Yeah. Why wouldn't it be thread safe if it's not changing the value?
Good question. Why wouldn't it be thread safe if it's not changing the value? It will change the value when you call the function again. If two functions call the GM time, it will get updated, and then it won't be the same. They're trying to use the same value, and you just are only storing it once. So let's say another one came by a second later. The first one might get that later time if it hadn't published it yet or whatever. So there's some issues with that. Yeah, Dave. Oh, good.
Since at this point we took out the sleep 2, what's the
Yeah.
advantage of making it multi-threaded versus having one?
Yes, we took out the thread 2 to make it multi-threaded. Yes. And is your question like, should we try it again with the sleep 2?
Or I guess since we took it out, what's the advantage of making it multi-threaded?
Oh, if I put the sleep 2 back in, it would be the, so here's what we did before. We just put a little thread, inside here, we put like a sleep 2 or whatever, right? So every time a server requests it, that server's gonna get it and then have to wait a little bit before it closes its connection. 2 seconds, as it turns out. If you have multiple clients coming in at once, then they will all get their own. They will still have to wait 2 seconds, as it turns out, but each one does not have to wait 2 seconds. Each one independently waits 2 seconds, doesn't have to wait for the other one to finish. That's the difference there. Yeah. Okay, so all of that said, we now have our good version, which uses threading, a thread pool, as it turns out, and it allows the server to accept a connection, spin off a thread really quickly, and then accept another connection. So if there are 100 connections coming, well, if there are 4 in this case, connections at once, it will very quickly deal with them. It's already pretty quick, but it would very quickly deal with them and not have to wait for the publish time function to end. Okay? So that's the big deal there. Now, let's see, we've talked about the publish time, there's the updated time. Okay, given the time now, I think we're going to talk a little bit about building a client. I don't know, we might get a chance to build the client. But I want to show you a little bit more about I'm going to use Telnet to show you a little bit more about how the internet works. Okay, here's what I want to show you. Okay, so we use Telnet to go to our server. In fact, it's still running. Telnet myth 58 1 2 3 4 5, and oh, maybe not. Hang on, maybe we had the I bet we still had the delay in there probably. And there we go. Yeah, we still have the delay in there. So we used Telnet to do that. Telnet, again, simply opens a connection and then has a plain text communications with the server. Okay? So you could do the following. Telnet google.com, port 80. Well, we know that the internet is on port 80. And if you do the following, you do that, we are now connected to Google. Okay? Now, we're not connected to Google's like pay server or whatever. We're not connected to like their internal network. We're connected to the website, just like your browser. This is exactly what your browser does. Okay, your browser says, hey, connect to Google. So that's that. There's a bit of a timeout, so hopefully I'll do the rest of it fast enough. But how do you do this? If we want to request a web page, you have to do a very particular protocol. And the protocol is HTTP, which you may or may not have heard about before, but it's the protocol which is talked on by the entire internet. Okay? There's a few different versions of it, as it turns out. What you can say, though, is you can say get / which means the home page, and then you say I am using HTTP /1.1. There's 1.0, there's 1.1, there's 2.0 now. 2.0 you can't use Telnet for anymore. It's a binary format, so that's too bad. Sad face. But that's that. And then if you hit return one more time, there's Google's homepage. Okay, so that's the home page for Google that we've now got. And it's actually, believe it or not, smaller than you might expect. It's mostly JavaScript in there, okay? And it's kind of compressed, right? You can see that Google doesn't bother with new lines, right? Why would they bother with new lines? If Google is sending every query new lines that the browser doesn't care about, the browser could care less about new lines. It just knows go to the next thing, right? Well, if it sends 1,000 new lines, well, that's 1,000 bytes it needs to send to you and a billion other people that are requesting from Google right now. Google wants to minimize the amount of stuff it sends you because it has to pay for bandwidth. I mean, it's not like free, right? It has to pay for bandwidth, and a billion times 100 is a lot of characters extra that it has to send every day or whatever, or 2 hours or whatever. It also wants to do it fast. So the more new lines that get sent to your browser that don't matter are just wasted time sending you your query, and you don't want to have to wait for your query. So what does Google do? They get rid of all the new lines. They run what's called a minifier on their JavaScript, which kind of takes it all and does this for you. Like, the programmers don't write like this, right? You don't go to Google and write like, oh, you're not allowed to use new lines at Google, right? They don't do that, right? You can use all new lines you want. Then when they run it through this minifier that actually produces this so that that's what you get. Okay, but that's how you get the details from Google. Okay, we can also telnet to web.stanford.edu port 80. Right, I'll do it up here. Okay, same sort of thing. This actually has a slightly smaller timeout. If we do get, and then you can get the actual one, class/cs110. It actually requires a slash at the end. It's very particular. You always wonder why in 106A they tell you have to be exact, or 106B, it's got to be the exact output. This is why. Computers talking to each other. It's exactly the reason. Let's make time out. And then if we type it without the slash and say 1.1, most web servers require that you actually say which host do you actually want. Google, for some reason, didn't require that, although we could have done it. Stanford.edu. And then one more, there we go. What does it say? It says, oh, I'm sorry, your document that you asked for, which was the one without the slash on it, /class/cs110 without the slash, has changed and gone to /class/cs110/. Right? It doesn't figure that out for you. It just says you did it wrong. And so that's why we did it. So let's try it again. And then this is still Stanford. We're going to get /class/cs110/ okay, http/1.1, and then host web.stanford.edu, and there we go. There's our web page for the class, right? And that's you can look, it's exactly the HTML and like the JavaScript and whatever for the class. It's probably not the JavaScript. Many web pages load external resources too, and your browser has to figure all this out. Your browser says, let me load the main page. Oh, is there anything else I need to load? And it goes and loads that, and then that tells you more stuff to load. And it's this big. That's why it takes some time sometimes for these web pages like CNN.com, which has a billion different files it wants to load onto your computer, mostly ads, I will say. And then it takes a while to do all that. So that's that. Okay. All right. Anybody have any questions about the protocol right now? We're gonna build a little client to do this protocol. In fact, we might as well do the client. We're also going to start building a program called wget, which is built into your program. If you do wget google.com, what it does is it actually goes and requests the web page just like we just did. It's pretty simple as it turns out. If we look at index.html, there's the Google page again that we just did. So you can pull pages from the terminal all you want. Question?
Yeah, so when I type a URL in the address bar, is it doing something similar to get, or?
When you type a URL in the web page, it is doing exactly a get.
Okay, cool. Because when I leave out the slash in like CS110, it figures out how to redirect it anyway.
Yeah. Well, notice that's a good question. The little message that came back and said your thing has permanently moved. Well, your browser goes, oh, that was silly. I need to put the slash on, and it just does another GET request and gets it with the slash. There are lots of error messages that come through your browser that are all hidden from you because your browser goes, oh, I can figure that out. That's one of them. Good question. Okay, what I'm going to do is client.starter, to time client.cc. Yes, okay. Time client.cc. This is actually relatively straightforward. Okay, we don't have to do too much for the time. This is just saying how to, the first part is just saying how to actually get the information here, or how to get the parameters for the from the command line. Okay, what we're going to do is we're going to do int client socket this time, not client, if I could type right, client socket equals create client socket argv1, and we're going to convert the other one to a argv2, convert it to an integer. Okay, so that's going to create the client socket. Okay, we're going to just assert that it actually worked. Client is greater than or equal to 0. Okay, you could do some better error checking if you want to on this. Okay. Let's see. The client, yeah, you're right. It should be client socket. You're right. I don't know why that's actually wrong. So client socket. Thank you. All right, it should be greater than 0. Okay, and then we are going to do sock buff and SB, because this is what we're going to set up just like we did before. Because all we're going to do is we need to be able to get the information from the server. Okay, IO sock stream and SB, oops, SB like that. And then we're going to do string timeline, we'll say, and getLine. That's nice, so we can just do getLine. Takes the socket server and then takes in timeline, and it just basically reads it in. Okay, and then we print it out, timeline, end L, and that's it. So there's our first client. Okay, if I didn't make a mistake, that's what it should look like. Okay, make time client. Uh-oh, lots of, oh, I know why. Client, thread pool. Do we have thread pool? We shouldn't have thread pool in here. Hold on. Make time client. Oh no. Oh, assert was not declared. And there's lots of other stuff in there too. Let's see. How about pound include assert? How about C assert? C assert. Let's see if that works. Nope. Did I do something else here? Let's see. I think you're right. Hang on. Let's see. Sock buff that. I never declared SS. You're right. Thank you very much. How about we do that like, oh no we did. Oh, you're right. Thank you. How about that? We need to call the constructor on and call it variable. Oops. Timeline. Timeline. Oh, perfect. Okay. Thanks. Oh no, same thing. Hang on. Well, now it seems to say it's up to date. Oh, maybe the other thing was broken. Time client, and then do we still have one running? We do. Myth 58, 1, 2, 3, 4, 5, and there we go. Now we got the time. So we made it. But anyway, the point is that a client is actually not that hard to build, right? You all you really need to do is say create a client socket and to a particular machine on a particular port, and then get the information to send you back, right? And that's that. Now you could connect up the connection and then have to send more information. That's fine too. But you could still do it this way. So it's relatively straightforward to set up a client. And now you have two different computers talking to, in fact, I think they're both on the same computer here. But you could have two, you could do this from your computer as well at home. And your parents could do it wherever they live. Yeah?
So when we set up the client versus setting up the server, it seems like it's more or less the same thing?
It's more or less the same thing. It's a very, it's not perfectly symmetric, but it's a relatively symmetric thing. You're setting up the I'm going to listen server. I'm setting up, I just want to make a connection to you and say, please send me some details, some stuff. That's the difference. One is setting up a server and then waiting for connections. That's the server. The client is saying, I'm setting up this connection and then immediately connecting to it. That's the difference. To a particular one. Okay. All right. If there are no other questions, we'll see you all Wednesday. Talk to you then.